Thanks a lot for the invitation, and thank you everyone for being here on a Sunday noon. So today I want to share some results on polynomial chi-binding function for t-broom-free graph. This is joint work with Xiaonan Liu, Zhaosha Shuder, and Xingxing Yu. Yesterday, Vede already gave a very nice talk on this topic. So a lot of the background are the same. So this saves some time. So hopefully we can go into the proof. So let's still go over the concepts really quickly. We say a graph to be H-free, where H is a family of graph. If a G has no induced subgraph isomorphic to any graph in H. Okay, so here we are talking about a forbidden and induced subgraph. The chromatic number is the least number of colors needed to proper color graph. The clique number is the largest complete subgraph, size of the largest complete subgraph you can find in G. And then if there's some, so we know the chromatic number is lower bounded by the clique number, and then the question is, can we upper bound the chromatic number by a function of the clique number? So if for some graph class, there's such a function where chi of G is upper bounded by a function of the clique number, then we say this graph class is chi bounded. And then F, we call that the binding function of that graph class. Okay, so we know not in general, we can't say all the graphs are chi-bounded, basically by the construction of Tat and also Michalski. So for a fixed clique number, the chromatic number can go arbitrarily high. And also this probabilistic construction of Odish also say that there exists graph with arbitrarily high chromatic number and high girths. So that implies if we have a finite family of graphs that we want to forbid, then this H-free graph will not be chi-bounded in general unless this H contains a tree. Okay, otherwise we have a construction with arbitrarily high chromatic number. Okay, so then so we know it has to contain a tree, and then this is this well-known conjecture by Yafas and Sumner, saying that actually for every tree T, the class of T-free graph is chi-bounded. Okay, so there are a lot of progress on this problem. In particular, I want to highlight this result by Kierstead and Panreis, which generalize the Yafas Semeradi Tuza's paper. It's true, this Yafas similar conjecture is true for all trees of radius 2. Okay, and then it's also true for some other spectral structures like double brooms, multi-brooms, and so on. Okay, so yeah, and then after we know a graph class is chi-bounded, and then the next natural question is, what is the binding function? Okay, so we say a hereditary graph class is polynomially chi-bounded if the binding function is a polynomial of omega. And then this is a very bold conjecture by S. Perret in the thesis. It said that every chi-bounded hereditary graph class is also polynomially chi-bounded. Okay, so far we don't know any chi-bounded graph class that is not polynomially chi-bounded. So this, we don't know whether this conjecture is true or not. Okay, but it will be nice if it's true. Another remark also mentioned by Vida yesterday, that polynomial chi-boundedness, if we can prove a graph class is polynomially chi-bounded, that will imply that the Odish-Heino conjecture is also hold for that particular graph family. Okay, so this is a stronger statement than the Odish-Heino. All right, so one of the most basic polynomially binding graph class is, we all know, the perfect graph, which is the graph family with binding function f of omega equals to omega. This is the best possible. And then we know a hole is an induced cycle of length at least 4. An anti-hole is a graph whose complement is a hole. And then this well-known strong perfect graph theorem proven by Jastrzewski, Robertson, Simon, and Thomas. A graph is perfect if and only if G is odd holes and odd anti-holes free. Okay, in particular, P4 free are perfect. Okay. Now there's a connection between Ramsey number and some binding function for some particular graph class. In particular, if you look at K1T, the smallest chi-binding function for K1T free graph. So this F star omega denotes the smallest chi-binding function. This is upper bounded by Ramsey number of T omega, because the maximum degree is upper bounded by Ramsey number of T omega -1. Right? In particular, if we take the largest degree vertex, right, and then we know the graph, the clique number is at most omega, so the neighborhood will not have a clique of omega. Otherwise, we have an omega +1 clique. So it must have an independent set. Then by the definition of Ramsey number, it must have an independent set. Then we find a K1T. So the maximum degree is bounded by this Ramsey number, and therefore the chromatic number is also bounded by the Ramsey number. So this natural connection between K1T free and then the Ramsey number. In particular, K13 is called a claw. So why do we mention K1T? So we know that a Ramsey number is polynomially bounded. And then, so if we look at both K1T free graph, in particular, both K1T free graph and P4 free graph are polynomially bounded. So the next natural question is, okay, what about the larger graph class containing both of them? Okay, so the immediate superclass of the both. So here the natural question is, what about the immediate superclass of both graph classes? So what is the, sorry, if the slide's moving, okay. Yeah, what is the immediate superclass of both classes? So if we try to extend a star K1T and also a P4, then this gave us exactly the picture on the right is the t-broom, right? This is the graph obtained from K1T+1 by subdividing an edge once. You can find a P4, you can find many P4 in here, and then this is also larger than K1T. In particular, if there are only, let's say there are only a two-broom, let's say T equals to 2, is also often called a chair or a fork. Right? If we draw the picture in different ways, it looks like a chair or a fork. So we know this graph, both of these graphs have radius 2. Okay, so by the Kierstead-Penrose result, it is chi-bounded, but it is so this graph class we don't know. It was not known whether it is polynomially chi-bounded. Okay, so it is so yeah, this is exactly what we study here. So this question was made official in the survey paper of Schimmer and Renderath. They ask, in the case of chair-free graph, okay, where we only have two leaf on the right, does there exist a polynomial chi-binding function for the family of chair-free graph? Then since then, there has been some very active research on this topic and on some subclass of chair-free graph. In particular, Chasnovsky, Huang, Karthik, and Kaufman show that if we addition forbid K to 2, then we have a linear chi-binding function, 3/2 omega of G. And then Karthik, Kaufman, and Sivaraman show that if we forbid some 5-vertex graph with a stable set of size 3, then it emits a quadratic chi-binding function. In particular, in the same paper, Sivaraman conjectured that the class of chair-free graph is in fact perfectly divisible, which can be split into a perfect graph and a subgraph of clique number size omega -1. And then as a consequence, this will emit a quadratic chi-binding function. Okay, any questions so far? All right. So what we want to show here is that we want to show that the class of t-broom-free graphs, which contain the chair-free graph, are polynomially chi-bounded. In particular, it is little o of the clique number to the power of t+1. Okay, is coming from this little o coming from the Ramsey number. And then when t equals to 2, let's see. Okay, when t equals to 2, we confirm partially confirm Sivaraman's conjecture that for chair-free graphs, the binding function is indeed quadratic. Okay, you can see that it is strengthening of the first theorem. Okay, it is quadratic. And then if in addition we forbid KTT, we can lower the binding function a little bit. Okay, if we forbid KTT, then it's little o of omega to the t-1 plus 2 over t+1. Okay, so that is the thing that is our theorems. All right, so with the remaining time, we want to kind of give an idea of how does the proof work. We are going to prove the first one, okay, and then mention what is the change for the quadratic bound. So we are going to prove that for all t-broom-free graphs, the chromatic number is polynomially bounded, okay, omega of g to the t+1. Okay. Before that, some familiar notation so that we are on the same page. Given a v in the graph, the neighborhood of v is denoted by ng of v. The ith neighborhood is ni. Given a set of vertices S, then the ith neighborhood is denoted by ni of S. If the superscript become at least I is the ith neighborhood and beyond. Okay, and then given a vertex and the set of vertices, V is complete to S if V is adjacent to every vertices in S, and V is anti-complete to S if V is adjacent to no vertex in S. So it's completely no edge. And then if it's not, if there's some edge and then some non-edge, we say V is neutral to S. Okay, so that is the language here. So similar to many proofs in this field, what we do is try to get some structure out of t-broom-free graph, and then if we can get a nice structure out of it, we can use induction or polynomially bind some parts of the graph, and then to do the coloring, okay, in the most efficient way. And then again, this is a kind of a standard technique. We want to take a maximal subgraph out of the graph. Okay, take some maximal structure out of the graph, and look at this first neighborhood, second neighborhood, and beyond. And then if we can get a good structure out of it, we can do the coloring. So the maximal graph we take is this Q, okay, which is a maximal complete Q-partite graph with one part, okay, VQ is an independent set of T vertices, and then the other part are single vertices, but it's a Q-partite graph. So it looks like that. Okay, look like something like this. And then we want to look at is the first neighborhood of Q and the second neighborhood of Q, and hopefully get some good structure out of it. So let's look at the second neighborhood and beyond, and it's easy to bound that. So we claim that the maximum degree of the second neighborhood beyond is bounded by some Ramsey number, which is polynomial, right? So it's easy. So let's try to see. Suppose this is an example. Suppose some vertex in the second neighborhood have a large neighborhood in the second neighborhood or beyond. Then, so suppose this vertex V have a large neighborhood, right? Then let's look at this vertex U, and then basically, if U has very few neighbors, if you have very few neighbors in here, then we can get a get a t-broom by looking at this structure. Right, and then if U has a lot of neighbors in the neighborhood of V, then we can also get a t-broom, because first of all, observe that U cannot be adjacent to everything here. If U is adjacent to everything below, then we can add U into the Q to get a more maximal, to get a larger complete Q-partite graph. Right, so U has to be non-adjacent to some vertex in here, and then we can get a t-broom out of this. Okay, so it's easy to bound the maximum degree of the second neighborhood and beyond. Well, and then let's now look. We can just look at the first neighborhood. So again, the goal is for some part of the first neighborhood, we can easily color it using polynomially many colors, and then the other part we'll use induction. And then so this induction and plus this polynomial many colors, then this will still give us a polynomial. So that is the idea. So we are going to partition the first neighborhood into several parts. Okay, these A, B parts it's very easy to color. We are going to color it polynomially. Okay, what is B? B is the vertices is complete to all these singletons. Okay, it's going to complete to V1 to VQ minus 1. Why? So let's collect all these vertices. Why are they polynomially colorable? Well, the maximum degree has to be bounded. If the maximum degree is very large, then we'll be able to find by Ramsey number. We're going to find a large independent set in the neighborhood, and then you can see that well, all these vertices are connected to V1 to VQ minus 1. So again, we can put these two into the Q to get a larger Q-partite graph. So therefore, the maximum degree has to be bounded. So the chromatic number is also bounded. The second part, A, we want to consider the vertices that are neutral to this VQ. Neutral to VQ means there's a neighbor and also a non-neighbor to VQ. Let's collect all of those. Okay, we want to prove the size of these vertices. Also, V is also not complete to everything there. Yeah, actually, the complete part is already handled by B. So V is not complete to V1 to VQ minus 1, and it's neutral to VQ. There shouldn't be many of vertices in A. Why? So let's for each of these vertices, we can record some label. So we can record which vertex in VQ is not adjacent to, which vertex in VQ is adjacent to, which vertex in this part that it is not adjacent to. So we have a label here, and then how many labels are there? There are VQ has size t, so there are t squared times omega of g many labels. Well, if A is too large, then by pigeonhole principle, t vertices. So there will be if A is larger than this number, then we'll be able to find many vertices with the same label, which implies by Ramsey number I will be able to find an independent set with the same label. Then you can see that this will give us a t-broom because all of them have the same non-neighborhood and neighborhood here. We get a t-broom. So the size of A is bounded. So now the remaining part, if I take away A and B, so A and B can be polynomially bounded. The remaining part is either complete because I already removed all the neutral vertices. It's either complete to VQ or or anti-complete to VQ. So we are going to color this part using induction. Okay, using induction. But again, the difficulty is that we cannot apply induction twice. If we apply induction twice, then it will give us an exponential bound, right? So we have to do the induction on this whole thing at a single time. So therefore we have to get more structure out of Z and W. What is the structure between Z and W? So here for the W part, okay, we have Z, which is complete here. We have W, which is on the right. We are going to split W vertices in W depending on what vertices in V1 to VQi, VQ minus 1 is adjacent to. So let's fix a bunch of vertex I, and then we are calling Wi the vertices that are adjacent to exactly the vertices in I, and then it's non-adjacent to all the rest. So every vertex can be labeled with the Wi. And then the claim here is that for any different Wi and I prime, the Wi and Wi prime, they are anti-complete. There's no edge between Wi and Wi prime. Okay. Otherwise, if there's an edge, we can find a t-broom. Okay. So Wi and Wi prime are anti-complete. The other observation here is that for every vertex in the Z part, which is adjacent to VQ, it has to be complete to every Wi. If it's not complete to every Wi, which I can assume Wi is connected, we just analyze each component, then we can find a t-broom. Okay, that is why we have this VQ here. So each vertex in Z is complete to Wi. And then also, one more thing is that, so basically each of these components Wi will split Z into two parts. right? The vertices that is adjacent to that xi and the vertices not adjacent to xi. So, and then the remaining observation is that every time I split z, these are complete. Okay, these are complete. Otherwise, again, we can find a chair. So, so what happens? Basically, we have this w, we have this z, and then each of the wi will cut the z into two parts, and then the two parts are complete to each other. So each of the component here cut it into two part, and then but because of the nice structure that these parts are complete to each other, we can apply induction. And then also we have this observation that each of this component here is either complete to some part or not complete to some part. And then the edges here are independent. Okay, this component here are anti-complete. So this basically we break this first neighborhood into complete and anti-complete parts. And then also the clique number here, because is at most omega, because they are all complete to each other. So the clique number here is all omega. And then also for some parts here, if we combine the parts that is adjacent to this clique number is also bounded by omega. So therefore, with this structure in mind, basically we can do the coloring. So let omega I denote the clique number here, and then for each component we use omega. Also use omega I, capital I, to denote the clique number here. And then the idea is that just we color all of this. Let's say using each of this by induction is upper bounded by f of omega I colors. And then for this remaining, for this component is connected to something, well, we just use the colors that is not connected to color this component. Okay, and then all in all, because of the nice structure, basically we can apply induction to both z and w at once. And then so the idea is that the chromatic number of the first of this part upper bounded by f of omega minus 1 plus f of 1 by the convexity of the polynomial function. So that guarantee that we only apply induction once. Then the remaining proof are easy. The chromatic number of G is upper bounded by some polynomial, which is the A and B part that we removed, plus the induction part. Okay, so the function will be some induction part and then plus polynomial, and then we can pick this f of omega to be 1 degree higher than the largest polynomial here. So here, if we look at the degree here, this is Ramsey number of t omega, which is little o of omega to the t minus 1 times omega, which is omega to the t. So then we can pick f of omega to be omega to the t plus 1. So so that finished the proof. So this is a quick run through of the proof. For the chair-free graph, essentially this part is the most expensive part. So essentially for the chair-free graph, we show that this A part is the union of two perfect graphs using the strong perfect graph theorem. So it is improved to 2 omega, and then 2 omega then together with the induction give us a quadratic bound. So that is the idea. Yeah, so there's after the manuscript is out, there's a new progress by Scott, Simon, and Spurkle. They proved that if I, instead of having one leaf here, if I look at a double star, then it is also polynomially chi-bounded. So basically that all the trees with diameter 3 are polynomially bounded. And then for anything beyond will be quite hard, which is P5. Okay, it's diameter 4, and then also we don't know whether it is polynomially chi-bounded. And then actually for all the Chino conjecture is also open for P5. So some open questions. So we have for the chair-free graph, we have a quadratic bound. However, in the Schremer and Render-Rath survey, they seem to informally conjecture that the optimal chi-bounding function for chair-free graph are the same as the class of claw-free graph, which the claw-free graph is R3 omega, which is little o of omega square. Yeah, so yeah, is this true or not? So that would be something. And then Silverman conjecture, the class of chair-free graph is perfectly divisible. So it would be nice to know whether that's true or not. For the t-broom and KTT free, we have this omega to the t minus 1 plus some fraction. I believe that this fraction can be removed. So can we improve the chi-binding function to omega to the t minus 1? Okay, and then also the ultimate question: does P5 free graph admit a polynomial binding function? Yeah, so that's it for me. Thank you.